Hello and welcome to the InterPlex. Jaishri Sanwal Bhatt is an Indian geologist and paleoclimatologist currently working at the Jawaharlal Nehru Centre for Advanced Scientific Research, JNCSR, in Bangalore. She is also deeply committed to scientific advocacy, outreach, and communication. For over 2 decades, her research has focused on reconstructing long-term climate change and active tectonics using cave archives and geological proxies, principally through the primary research tools of paleolakes and speleothems. The main geographical areas of Sanwal Bhatt's work have been in the Indian and Nepalese Himalayas, the Andaman Islands, and the eastern and western seaboards of India, and her research addresses questions that sit at the intersection of earth science, water security, and natural hazard assessment. In our informative, wide-ranging, and interactive InterDialogue, we spoke about deep geological time, the importance of interdisciplinarity and more effective science communication, her work in organizing science outreach programs in rural India, and much more.
Hi, Jaishri.
Hi.
Very nice to be here in your lab with you.
It's a great pleasure to have you here in our lab and in our institution.
It's been a great visit. I've appreciated all of your efforts. Thank you so much.
Thank you so much for your such a wonderful talk which you gave here. Many of our students, I'm very sure that they got inspired with. We are already impressed with you.
Oh, no, please. But
with your work, especially the kind of work you are doing with the community, and because it is not very easy to commute, with the communication with the community, because scientists have a different word, and then those knowledge communicating with the local people, sometimes they don't understand. It is not an easy task, so it's wonderful.
It is certainly a challenge, and we all share in this effort and appreciate your efforts very much as well. So I would like to ask you a bit about, your work, but how you got inspired to be a geologist and especially a female geologist and field worker here in India. What excites you so much about geology?
Geology, actually this story starts from long back when I was a small girl. So as you asked me how I got inspired with or how I got motivated with, so I always had a great interest for geology. My father was an electrical engineer, so he used to go to different places, he used to travel a lot, and that too by foot, the trails and all. So I was very fascinated to go with him because I love seeing the different landscape, going along the rivers, going along the mountains. He was posted in Himalayan region, lesser Himalayan region, a place called Munshiari. It's in Uttarakhand, Himalaya. So it's in the higher Himalayan region, and we used to have snow for 6 months, and 6 months are the time when we could go around the villages. So I always go with my father, and I always carry a bag. What my mom used to do, she used to give me some food. She will pack me some food, and as soon as we start our journey, I'll finish everything so that I can pack my bag with a lot of rocks. So whatever rocks, can you imagine a girl like 8 or 10 years and then walking along with my father, and whatever rocks I will find that beautiful, I'll put them in my bag. So after, about 2-3 kilometers after walking with my father, the bag used to become very heavy. And then again, my father will ask me, what now? Throw them. I says, no, please, I'm not going to throw them. Then every time he has to carry back those, stones. And whenever my mom will wash my clothes, she will find one of the other stones in my pockets. But I didn't know, I was fascinated to see the beauty of rock. And I always used to wonder why the mountains are so high, and within the mountains, how the deep valleys are carved, all those things, and how the lake has formed here, how the water bodies. So I was always used to ask questions with my dad, and whatever with his limited knowledge about geology or about the geography, I should say, he used to give me some answers. And then once I was walking with my father on a trail, so I found an old fossil. Then I asked him, what is this? So this was a fossil, and those like the animals which lives only in the ocean. So he gave me certain clues about. Then I was wondering how how the fossil, it has got into that rock, which are now so high. But that time I didn't get my answer because my father was also not able to give me the correct answer. But he had little idea about that there was a sea, and probably, the sea sediment has lifted up and now you see them there. But that remained in my mind, and when I grew up, I tried to search some of the other way to get connected with this science, especially the science where we study the rocks. But unfortunately, we don't have any such subject when we do our degrees, when we do our high school or intermediate. But when I went to my college, then I got introduced to the subject. But since I was a girl, so there were a lot of things that I cannot, like professor also told me that this subject is not for the girls to study because you have to do a lot of field work. You better go to the, you take chemistry or other subject, but not geology. So but I requested him, and then it happens that I follow up for 3-4 days, and finally he let me in, and then I did my geology in bachelor's, and same thing happened with master's. Now again a drama happened when I wanted to do my master's, because the place where I study is again in Uttarakhand, deep. It's a sort of a very small town in Uttarakhand. It's called Pithoragarh. So we had only the graduation, and ours was the first batch. So we have no masters that time. So for masters, I wanted to go away from my parents. That was the only thing. And my father was not ready for that.
I see.
Our time was a little different. We come from a little orthodox, I should not say orthodox, but little backward families like where they do not send their daughters far away for the studies. He said, when you have options here in biology, or even you can study other subject, why you want to go that far for studies? But I was a little stubborn, and then I persistent that I want to do geology, otherwise I will not study. So then finally he has to accept, and I went to Nainital to do my master's. I did my master's from there, and that's how the interest, it became my passion became my interest. It became my sort of, job. I started my PhDs, and I got a lot of chances to interact with, because when our department, geology department in Kumaon University, used to host a lot of big professors, like well-known professors that time for lectures, and we used to interact with them a lot. We get to know, and as I started growing up, I think my interest in geology also started growing up, and I got deeply connected with the subject. It's not only that because I want to do PhD, I did it. It was all about my interest. I wanted to learn more, and I did. Then I did my PhD. So this is
a lot of passion for the subject.
This is how,
and you proved that undergraduate professor very wrong, right?
Yes,
Who told you couldn't do it. Right?
Yes, I proved him wrong that geology doesn't ask you what is your gender. Right. It's only we human, we decide this subject should be pursued by this gender and this gender. But rocks never asked me. Still, rocks has never asked me which gender I am. So I continue working with geology.
Great. Okay, so one thing very fascinating about your work, geology in general, but especially about some of what you work on, is sort of this way of piecing together epochs of history. You're able to track tsunamis and earthquakes even through rocks. And you've explained to me your techniques of taking lake cores and also stalagmites.
Yes.
So can you explain this sort of what I would call big history type of approach, connecting different epochs in a panoramic view of where we come from, origins, and what are you able to trace through the rocks, and how does it compare to some of these other methods of taking cores to then piece together climatic, hydrological, or extreme events as well? Yeah.
See, as you said that how the history, how we all begin with. So our Earth itself has begun with a long history. So if you see this, a small poster here, so after the Big Bang, so it's just like us human, like we evolved through the ages. We are not what we born, years back. So like Earth was also, when the Earth was born, started, and then there was a long evolutionary history of Earth also. But when Earth came into solar system, about 4.6 billion years old. The oldest rock has been dated around 4.6 billion years. So this is a story of all, how it all evolved. So initially you don't have any free oxygen for any sort of species or animals to survive or even emerge. So slowly the oxygen came into the picture around Precambrian time. So these are the geological scales which you can see, like Cambrian, Precambrian, Ordovician. So all these are the geological scale. So all these geological scale have demarked by some sort of extension of the animal or emerging of a new species. So some mega event, we should say, some mega geological event that makes the boundaries, the stratigraphic boundaries between different periods. So the oxygen started coming into the Precambrian, and here in front of you, this particular rock, which is known as stromatolite, they are basically the cyanobacteria. Okay. So they started emitting oxygen, releasing oxygen into the environment much earlier, because before it was all methane, and then you have anaerobic conditions. So this was called an oxidation event. Okay. So during oxidation event, when these species started emerging, they are the algae, cyanobacteria, blue-green algae. So when they started emerging on the land, then they released oxygen, and that sort of made the base for life to start in the oceans. And then because that ocean was also not like blue like today you see. The ocean was full of different gases, toxic gases and all, and it was used to look like a green ocean, not like blue today. So then slowly what happened, whatever the dissolved iron was, because there was a lot of dissolved iron and other oxide or other minerals were there. So when they started releasing the oxygen into the ocean, so it became iron oxides. So then you have these kind of rocks. So the iron started interacting with the oxygen, and it became iron oxides, a little bit heavier, then started precipitating at the bottom of the ocean. So you make these kind of rocks that time. So this rocks is what you see here, the lighter color mineral that has been bleached out, and then these red ones are the hematite or iron-rich sediment. So this is how, and then they make the base for life to begin with. So that's how the beginning of the life happened with such kind of invertebrates. So this is a fossil of trilobite. You have more fossils before it came, like Dickinsonia and Ediacara fossil, all those things started, and this was a primitive life which all started. And
you said
animals,
that was about 300 million years old?
Yeah, 3.452 million years old. Okay. And then these kind of ammonoids started coming in. Then slowly all these invertebrates came first, and then it got evolved into vertebrates, and then the life came onto the earth, on the continent, from the ocean, and then it evolved. And then in between you have lot of mass extinctions as well. And a lot of volcanic eruptions were happening, during those days, that time in the past geological time. And then the same time you have a lot of volcanic eruptions and the meteoric fall, which many a times which covered the earth completely. So the sun did not penetrate it on the earth. And then you have warming event, the greenhouse effects, the warming event, and slowly it turned into our earth turned into the ice balls. So there were many events when our entire earth turned into the ice ball events. So this is how our earth has evolved. We are actually very young. So if you see this chart here, the spiral here, so we are here. Just 1.6 million years ago we came. And see in this small time period what we have done to our earth. We are just exploiting our earth, which is actually not good for us. So many millions of years, it's a history of earth, and we are just destroying it. So this is how our earth evolved, and we are very new, quaternary period. So my research is mostly focused on this period, which is quaternary period. And I started my PhD looking for the lake sediment. So we did the reconstruction of climate So the section which I worked was a paleolake section, around 35,000 years old sediment.
This is the core.
This was actually an exposed section because it was a paleolake. So along the roadside, the section was exposed. Then we took the sample. Each centimeter we took the sampling, and then I use a lot of data, geochemistry data, and the proxy I used as lake deposits as a proxy. I started, like when I began the career, I used the lacustrine sediment, and then using those lacustrine sediment, I did a lot of chemistry, like I did carbon and oxygen isotopes of those sediments, and then I did some geochemistry, like some mineral composition, clay minerals, how the clay minerals are varying. For if I have about 12 meter thick sediment. So if I start the sampling from the bottom and I go towards the top, so each centimeter I have to drill this, I have to take the samples out, scoop it out, and then we do the analysis, different analysis, like as I said, geochemistry and stable isotopes, clay mineralogy, and I also did some patches. I got fossils also, microvertebrates. So I did some studies on microvertebrates. So they also indicate us what kind of climate they were living in, what kind of environment they were living in. So we reconstructed the environment during the animals were there, what kind of environment they were, and at the similar time we also reconstruct the entire history of 35,000 years. Climatic history, precipitation history, how the precipitation varies during that time. So we covered a lot of mega event like last glacial maxima, then you have younger dryas, then there are many more such climatic event when the climate was very dry for a long time, and sometime the climate was very wet, sometime it was very cold. So these kind of event got captured on those lake sediments.
How were you able to determine that, the precipitation patterns?
The precipitation patterns,
the
mostly we use, what we have used here is like the carbon isotope. So carbon isotope, what happened? Carbon isotope gives you a signature about C3 and C4 plants. So when you have more rainfall and humidity, that time you will have a lot of C4 plants. But in the other case, when you have little dry conditions are coming up for a longer time, then you have more of the dominance of C4 plants. So based on C3 and C4 plants, we can reconstruct the climate, whether it was a humid climate, precipitation was in a good amount. Then when I was doing this work, so I found that the age control, because we go for radiocarbon ages. So radiocarbon ages, we always have plus minus 1,000 years, like before to be precise dated, and even we have 100 years or 200 years of plus minus error bars. So that is huge in terms of climate when we are talking. So if I'm talking about what happened 3,000 years plus minus 1,000 years becomes either it is plus 1,000 minus 1,000. So it's a long period which is sort of missing the evidence, and there is no other technique that I can go for the precise dating in the lake sediment, because in lake sediment what happens sometime, if you have more rain, if the lakes are flooded sometime, you also erode some material and it gets mixed up. So these kind of problems I faced when I was working in the lake sediment. Then I started, after my PhD, from 2009 onwards, I started working in the caves, because the speleothems, which you are seeing here, so these are the carbonate deposits, sediment, secondary deposit of carbonates. They can give us an absolute age data. They have a very good age control. So here I started getting the age in plus minus 15 years, plus minus 20 years, plus minus 10 years. So a lot of improvement. And then it gives me the decadal scale data. Like whereas the lake data gave me about 1,000 years, so I interpreted in terms of what has happened, 200 years, like centuries data. But here I started getting the decadal scale data, or sometime even if we have good age control and we can count the layers, we can see, so it gives us the annual scale data also. So it becomes more precise. And when I started using speleothems, because there in the lake sediment, mostly what we can define is like Whether precipitation we cannot talk more about, it was more about kind of humidity or drier conditions or humid conditions, because the precipitation rate cannot be calculated that accurately, as compared to speleothems. So then I had in my mind that I want to do a little more on precipitations, that how precipitation variation happen and the hydroclimatic changes, I should say that. So then we started using, and I started getting very good result, very good data. And then when I started reconstructing the paleoclimate using these kind of speleothems, then I realized that they are also equally important for hydroclimatic conditions and recharge of groundwater. Because what happens when you have more precipitation, so a lot of water which is precipitating due to the rain, whatever you are having more rainfall, so that means it goes to the runoff.
Sure.
So not much water gets contribute to the groundwater. So these are the conditions now we are facing, because we are the kind of rain we used to have for 1 month, now similar kind of rain we are having sometime in a day or two. So most of the water is going into the runoff. So we are not able to calculate how much the groundwater are refreshing or how much they are getting refilled. So these kind of work, recently I started with the DST project, Department of Science and Technology project. So we are monitoring some of the caves in Kumaon Lesser Himalaya to see what is actual groundwater contribution from the precipitation.
So it's a way of connecting some of this paleoclimatic work with issues threats that are going on right now.
So I have some collaborations also with people who use AI and machine learning. So let's see if our data also can be combined with them, and if we can predict something, how the aquifers are going to have the recharge, in future, how they're going to recharge in future based on the kind of precipitation we have in the last 10 years, because now we have equipment data and then monitoring data. So based on that, if we can develop this. So we need proxy data, because last, if you see 50 years, we have instrumental data. So based on instrumental data, we know how much precipitation was there in the past 50 years max. Sure. But what beyond that? So if you want to talk something about the future, what is going to have, you need a long-term data, the past data. So that 50 years are not enough to predict what is going to happen. So that's why we need a longer scale data, which can go up to 50,000, 30,000, 10,000. So that gives you an entire picture that what has happened in the past and what is happening now. And then using those two things, your proxy data, your instrumental data, then there is a possibility you can utilize and then can do some sort of modeling what is going to happen.
And how far back do these go, these samples that you're taking?
Speleothems, so far what I have goes only 10,000 years, but there are people who have published some results, their data goes back beyond 12,000 years. So, but so far I have published, whatever published data I have, it goes only 8,000 years and 9,000 years.
And what is the scale of this data? This is more regional, you work in the Himalayan region, so it's specific to that particular region, what you're tracking?
Yes.
Okay,
yes.
Does it register anything related to global climatic patterns?
Well, more or less, if you see broadly, of course, it does matches with the global pattern, but the regional climate change has much more to play a role in it.
Sure.
Because even if you go for the dendrochronology, because we have a lot of secondary precipitation and even local precipitation in these regimes. So when we have valleys, we have more precipitation. So these kind of small changes. Lake data, if I'm using, of course, I can globally, because it's a longer data, it's a century data.
Right.
So that is more feasible for me to correlate it with the global cycles. But when I'm doing the decadal scale data or even annual scale data, annual scale precipitation, so it is not good from my side that I try to correlate it with the global. Of course, if I have the signature of, like I had in one of the sample, I got the signature of Little Ice Age. So Little Ice Age first was thought to be a drier kind of climate in India, where you don't have much precipitation and the summer monsoons, Indian summer monsoons were declined. So there was this kind of data was published from most of the part in India. But when we got the data, I got just, adverse result. I started getting more precipitation during the time when there was little ice age. So it was not acceptable for the scientific community, but then I have to struggle to publish it, and then once it got published, now that's the most cited paper, because then many people also studied in different regions and they come up with the similar results, that during little ice age, Himalayan were still receiving precipitation, because we have two regime, especially the western and central part of Himalaya, also received winter westerlies. So we receive southwest monsoons, which comes from the Arabian Ocean, and we do also receive the monsoon which comes from Mediterranean Ocean, the moisture which comes from. So the moisture that contributes during the summer, winter time, mostly winter time, in the form of snow, but it prolongs some time. So this year, if you see, for example, the winter westerlies are so strong, we are still having snowfall in the regions, some of the regions that contributes by the winter westerlies. So it justifies like why we had similar kind of patterns in the past also.
So it's a complex interplay of many different variables.
It's a complex interplay of two monsoon systems in Himalaya. It's not as easy as.
So that initially was not accepted by the scientific community, but you persisted, and now it's something that others are tracking in different regions.
Yes.
It's important. So this is some of your work in the Himalayan region. You've explained some of your work in the Andamans as well. Generally, I'd like to ask, how are you able to track or analyze the extreme events through rocks, whether tsunamis or earthquakes? It's quite interesting. And how are you able to see that, and what kind of rocks are you analyzing that actually have that signature?
Okay, so for example, let us start with the speleothem itself. So we have the growth perturbations in these samples, in these formations. So like if you see, this is a central growth axis. So what happened when you have earthquakes? So you have two kind of movement. You have horizontal movement and you have vertical movement. So whenever you have movement, it changes the position of drip water, and sometimes it does also change the position of your floor. So that gives rise to some kind of perturbations. We call it growth perturbations. So this was a central growth axis. So due to the a great event of earthquake, we can say that the entire this growth axis has changed, and which was depositing like this has shifted here and started growing like this now. And then it was growing then with no problem, no maybe big earthquake that time. Then there is another event of an earthquake here. So we also recorded this earthquake. We date them using uranium thorium chronology, and then we can accurately we can date the event of earthquake. So this is how we are doing the earthquake studies. So a part of this speleothem, we also use some sediment data, like from lake or some fluvial sediment also sometime, where we see the the faulting in these kind of big sections. So that also gives us the date of an older earthquakes, when it happens. So mostly we target the gantotic plains for that, and we see a lot of faulting, and twisting boulders sometime. And also, very interestingly, we have worked in some of the construction sites, like old construction temples, which were toppled during the great earthquakes. And even some of them are twisted, they are rotated. Their dome is rotated, twisted. So those things also we used to date the older earthquake.
How accurate, or like to what scale?
Because for us, it's like just not, we don't believe only on one proxy. So we use all these data together. Like we use speleothem, we use the sediment, and at the same time we use the buildings, destruction of the building. That gives us a complete story. And it is very interesting that most of our data overlap with each other with some difference, because we always have the error bar. So if you if you just navigate with that error bar, so they falls almost within the same brackets.
But the accuracy is on a scale of 10 years,
decadal scale, not more, because now we are using more precise data. So sometimes it gets us like plus minus 10 years.
And more generally, how does this compare to other techniques of dating from let's say, tree rings or from ice cores, or what are some of the similarities and differences in techniques?
Yeah, so we have done one study using the speleothem data and tree rings also. We wanted to compare, how it can be compared together. So, very interestingly, that we saw the heterogeneity in different proxies. So they do not match very well. In a broader scale, they do match. You can see the scale is matching, but if you go to the the closer interval or high resolution, then you find a lot of difference. So what happened when you talk about the dendrochronology, the trees, because they have soil moisture in that. So even if you have a dry phase for a few years, it grows because it takes some soil moisture and starts growing. Whereas in these speleothem, if the water will stop dripping for a few years, if the precipitation will stop for a few years, the drip water will decrease. And that will give some sort of hiatus periods here. Whereas in, if the precipitation is stopped for a long time, you don't have rains. Of course, in dendrochronology also you can identify the hiatus layer, but still you can identify those layers, very thin layers, the hiatus layers. But here they are very prominent.
I see.
In speleothems, they are very prominent. And sometime even what happened, the topmost layer, I have seen in some of the sample, it's really fascinating, how it works. So you have calcium carbonate, saturated water, which drips down and gets settled on the top here. So when you are having the sort of, drier period, so the drop will not fall here so fast. So it will make some sort of circles in the stalactite, which is feeding the stalagmite.
How interesting.
And then when it becomes more and more bigger, due to the gravity, it cannot hold its weight. So due to the density, it collapses here. And then because it's collapsing, though from a same distance, but it is much heavier than the one which is coming due to the precipitation, during the more precipitation. So you have a different kind of, sometimes it makes such kind of depression because it has a lot of calcium carbonate in it, and that time you have lot of other minerals, other trace elements also. So I use isotopes to analyze mostly I use oxygen isotope to understand the precipitation pattern in the past, and then the same time I also use the incorporation of trace element. So if the trace element incorporation is more, that means the climate is little bit more drier, because then water has lot of time to interact with the rock, it dissolves the minerals, other minerals, trace elements, and then precipitate. So sometimes it is very well seen in the structure, microstructures of the speleothem, as well as in the trace mineral composition. So you can easily identify, and it is very beautiful to see the changes. You see the change, you see the structural pattern changes in the speleothem. At the same time, you see that the mineral that trace element percentage is also higher that time.
And to see that correlation,
correlation, and it very well coincides and very well correlatable with the oxygen isotope data also. Many times.
Can you speak a bit towards lake cores? That was interesting.
Yeah.
What has been your work with lake cores, and what can they tell you?
Lake cores, we do face one challenge in lake core. First, taking the real core from the lake, because if we are taking the core from the proximal side to us, then we have sometime, the grain size more, and we don't get very good data, so we have to go towards the deeper side of the lake, and that becomes coring. In India, sometimes becomes a little problematic. We do not have that kind of facilities which you have in Europe. You can take a good lake core, and in lake, I did coring for Vular Lake in Kashmir. There I found a lot of reworking.
Okay.
So the older sediment sometime I found on the top, and the younger sediment I found at the bottom. So it was so much reworking that my paper is still struggling to publish for the last many years.
I see. Okay.
So these some problems we face in the lake core, but it's a very good proxy if we can have the lake core. So I tried, but I could not succeed. So mostly I worked on the paleolake sediment, which are exposed on the rocks. So I found them more interesting.
And as a proxy to what in particular?
It's a proxy for precipitation, like climate change.
Okay.
And as I said that if it's a lake sediment, then of course you can also understand more like a precipitation, but my concentration was mostly on the paleo lake sediment. So that also tells you the same story, but sometimes you have more erosions in those sections, so it is not so easy to find those kind of vertical sections at the roadside.
And I know this isn't something you've worked on specifically, but just for like an educational purpose, how do those then compare to ice cores, and are there things that ice cores can tell that lake cores are not able to expose, I suppose?
Well, yeah, that also happens because, as I said, lake cores. So lake cores, sometime when you have more precipitation, so even if they do not have a pathway where the water can go off, run off. So water can go off. Even if they are closed basins, so many a times you have a lot of reworking, which you don't have in the ice cores, because ice is just, it's got, it is layered, and you don't, only it is when you have hot summers and you have a lot of melting, then you lose some data. Otherwise, you don't lose much data here. But whereas if you see the lake sediments, sometimes you do lose the data. If more, depending upon the conditions, it is getting deposited. And sometimes you have landslides around the lake. So a lot of material comes, with the rains, and the siltation is more. So you won't believe, sometimes we get thick as 3-4 meter sediment that has been brought only by one event of flood or a landslide.
I think you had mentioned, I'm trying to remember what they were in, but water pockets that form at times in what you're analyzing, like water bubbles or something like that. I know in ice cores you'll have air bubbles where you're able to analyze the climatic composition. Is there, I don't know, was it in the rocks that sometimes there are water pockets that are preserved over time, or maybe
sometimes you even get in these speleothems also, and especially when you have more crystallization. I got in some samples that they were crystallized like calcite. So the polymers of calcium carbonate, you have calcite and aragonite. So you have phase transition for a long time. Like when they get settled first, they get deposited as aragonite. So due course of time, it changes into the calcite. So we found some water drops even in the drusive, those layers. You can also date that water. But that water was very small. But in some cases, the water get trapped within the crystals. So that can be dated.
And
so
does that have a certain composition that can tell you something?
Yes. Then they can also, because since you can date them when exactly this water, which period this water was deposited, and of course the chemical composition can give you about the conditions under which it was deposited. So these kind of information also you can gain if you are very lucky to get some water trapped inside the crystals.
Quite interesting. So back to some of your work specifically with understanding and tracking tsunami episodes and your work in the Andamans. How were you able to do that? That was quite fascinating. I think you said you were able to identify, was it 9 or 11 events over the past?
9 events we were able, including 2004 events. So very interestingly,
how were you able to do that?
As I was telling you that before 2004, what happened, because you have this Andaman Sumatra subduction zone there. So it's a subduction zone. So what happened? Subduction zone means one plate is going down beneath the other one. So sometimes it gets stuck, but still because plate is moving. So what happened? A lot of stress develops down there. And being an island, Andaman Island, the plate is very thin because it's an oceanic plate. You don't have a lot of sediment there. So this plate, it goes up. So what we saw before 2004 tsunami, that all the corals which were growing before beneath the water, they came up. So that means they are exposed. They are dead when they are exposed to the direct sun. And then earthquake comes, the stress gets released, and slowly the plate goes down again. And then when it goes down, again you grow them, again you grow the younger ones, the younger corals again grows there. And this goes on. The land goes up, goes down, goes up, goes down. So likewise, you get different kind of terraces. So terraces of dead corals. So you can date them accurately. You can date them, and you can know about how many events you can capture. The earthquake event, because it has come up, it has gone down, like that. Also, you can tell. And similarly, what happened when you have the bigger tsunamis? That time also, because it's a high energy waves, and it brings the water. It brings the sediment. The water brings the high energy water, brings a lot of sediment. It scours, it just scouring. It scours at the bottom of the ocean and brings all the material and dump it into the coastal region. So we get some kind of species which you don't normally get at the coastal side. So there are species of forams like Quinquequilina and other species which lives in the deep ocean. But if you are getting those deep ocean species at the coastal region, that means you need some agency to bring them here. So
That's
these
another
tsunami,
signature.
so this is another signature, and we have some more signatures, sedimentary structures. We have peculiar sedimentary structures which forms during the tsunami, because for us was when we saw the 2004 tsunami and we wanted to track it back, then how many tsunamis have happened in the past, and we started looking for all these kind of proxies, as I said, the corals and other proxy. Then we found the sediment, and we found some sort of lagoons which are sort of depressions in the coastal region, where during the tsunami the water comes along the sediment and get deposited here. The water slowly evaporates, but what left is a sediment. That sediment you can date, you can analyze, and that gives you the relative time of the tsunami, plus minus in some years, because mostly we go for the radiocarbon ages. So it gives you the data of about 100, plus minus 100 years, plus minus 50 years. Now it's more precise because it's, AM is dating.
How far back are we going for these known events?
For me, the work which we have done is gives you the history of about 6,500 years.
So
long history of nine events.
And how strong was this 2004 tsunami in comparison to the other 8 events?
Exactly, we don't know, but it depends on how far towards the land, inland the water has reached. Because if it's a large tsunami, then of course the water will reach more towards the land. If it's a tsunami, if it's a small tsunami sediment and not with lot of energy, so it may not reach up to the inland. So it depends on how much towards the land it has reached. So for this particular 2004 tsunami, we have done some modeling. So for modeling, we have first the simulation was done for 9.5 magnitude earthquake, and then simulation was done for 8.5 and 8.2 magnitude also. If this happened and the faults are behaving in a different way, then how far the wave will propagate. So that model also was developed for 2004 tsunami, because we know that how much the magnitude was for that particular tsunami. 9.5. So we did that, and then what we found that if you have if you have different kind of rupture, depending upon the rupture, the water will propagate towards. So then we found that if you have 8.5 magnitude tsunami, the water will not propagate beyond up to the African coast. But here in 2004, even the eastern African coast was also disturbed. The tsunami inundation, the waves reached up to African eastern coast also. So these are the kind of things where we are also using the modeling data and of course the geological evidence to understand the past tsunami.
Working together. More complete picture.
Yes, and it's very interesting as we are working for these speleothems, So what happened, for example, Andaman region. So there are a group of scientists who have worked there in the caves, coastal caves. So they found the tsunami sediment inside the cave and they preserved it.
Oh, wow.
The tsunami sediment. So they have also come up with, when I read that paper by Robbins, I think, so it was so fascinating. I also started looking something like that. So we have a project now in Andaman. So I really wish to see sometime if we have some kind of tsunami deposits inside the caves as well. They also gives us a lot of data about tsunami.
I don't think I asked you this before, but when you were describing the corals and how they get exposed to the sun, they die, and then there's a signature as they go back down, and the dead corals. Does anything like that happen to the forests as well, mangrove forests that get destroyed during So what signatures are there of past events, or even the 2004 event from dead mangroves, for example?
So when we did the field work in 2009-10, we started working in Andaman. So we saw that a lot of mangrove forest was completely destroyed by the water because because mangrove needs fresh water as well as the seawater to grow. But when they don't, all the fresh water is being cut off, and the seawater, got into their fields and even the mangrove forest. So mangrove forest was completely dead, including their cultivated land. Right. They had a lot of cultivated land close to the ocean. They also got destroyed due to 2004 tsunami. So they used to tell us, they says. Where we were working, one person also told us their experience, that their ancestors told them that they had built their house quite far off because they have some cultivated field there. They used to cultivate, but later on because they were not aware that it was tsunami, so they said something happened, and then wave came and destroyed everything, including their mangroves, including their land. Everything was dead that time. Everything being destroyed by the seawater came up. But then later on, for many, many years, there was no tsunami. So they started building their house close to the coastal area. Sure. And then now they had to face the consequences. Their house was completely, destroyed by the tsunami wave and the land and the mangrove. So then we also give some knowledge to the people that they should grow mangroves so that they can at least, save some of the community which are living very close to the coastal areas because they protect from tsunami waves.
And my question was also from the past events, the ones that you're able to see, the signatures from the coral, are there signatures from dead mangrove forests as well?
Yes, we do get, because we take cores. So in our cores, like maybe I'll show you some photographs. Beautifully, you can differentiate between, what is a sediment, tsunami sediment, and what is the normal sedimentation. We have roots of mangrove, and sometimes we have this thick, like about some few centimeters thick mangrove deposit. So we did some pollen analysis also, but we have not published in this paper because data was huge, and they asked us to give just cut off some data because you already have enough evidence to prove that they are tsunami deposits. So we have not used the mangrove pollen. Otherwise, we have a very beautiful evidence from mangrove forests which got destroyed during tsunamis, and we have those in layers. So as the corals. So what we find here in tsunami layers, as well as the sedimentation is concerned, we find the coarse grained sediment, and then upward winding sequence, and then we have these dead corals, broken corals, and then at the same time we find the foraminifers, and we find the sudden increase in calcium carbonate because a lot of shells also they die that time. They come and die there, and some coccoliths also nanofossils which lives only in the deeper ocean. That also we found in these tsunami layers. So it was very exciting for us to reconstruct because we find so many evidence, and every day we used to get so excited that wow, I found a new species today which doesn't live in the coastal region and it lives in the deep ocean, and we are finding it also becomes add on to the sort of evidence of tsunami. So it was very fascinating.
And it's very diverse and dynamic. It's fascinating.
And it's a very dynamic environment, you see. So many a times, the first fieldwork was, of course, was a success, but second time when we went, it was completely chaos because we couldn't find any such sediment. We did coring in a lot of places, but as you say, is that it's a very dynamic environment, so it erodes the sediment. So some of the places we have one event which was completely missing because the people started cultivation there. It was a little far off from the ocean, but we got all the older evidence, but just one event was missing because I think they have taken out the sediment from the top to do the farming there.
Well, I'm just recalling one interesting story. You told me that during the 2004 tsunami, some of the more traditional groups, the tribes there, they had an awareness of past events, and they went to highlands where the coastal communities were the ones that got their property damaged.
Yes.
Yeah,
I was telling you.
Can you explain that a little bit?
Yeah,
better?
what happened when we were working in Andaman? So we speak what we do. We do not isolate ourselves with the people. We want to know, so we talk to many people who ever understand our language. Mostly they understand very well Hindi. So they are Hindi-speaking people, and they tell us like stories, what had happened. So their parents would have told them that happened, that the high waves came and they destroyed their houses during that time, and their land where they were growing the cultivated land and where they were doing the farming, they were all destroyed. And even the mangrove forest, it shifted, because of course when you have a lot of water coming in from the sea, so that will die, and then they will start growing the mangrove forest towards the other side, towards the higher reaches. So what they did, because they knew that it is going to be, again it can happen, so they started migrating towards far from the sea, and towards little higher land they constructed their houses. But in generation after generation they saw there is nothing, and the sea has left a lot of land for them, and it was more fertile. Why to climb up that much? So they started again settling down into the coastal region, and that's why they have to face the consequences. It is actually the same thing. It is not only tsunami. If you see, even in Himalayan region and any other mountainous region. So what people now do, before our ancestors, I come from Himalaya, so our ancestors always used to make their houses on the hilltops. Not on the valley, because they know that valleys are risky for them to construct a house. But now, because they can't, I don't know, where they want to save the money, so what they do, they start making their houses very close to the river, sometime on the floodplains. So what will happen when you are constructing your house on the floodplain? Of course, river will not change its course. River has to flow, and then the house will be destroyed, and then they will claim other people. They will claim the government. It's not like that, They should have some knowledge, and they should carry the indigenous knowledge why people have started building the house far off from the river, not at the edge of or at the base of the mountain, because they know that these places are vulnerable for landslide. These places are vulnerable for floods. So they understood the nature much more than I think this generation, because we do not spend much time with the nature, so we don't understand.
Of course, and that's what happened in the Andamans. They were the indigenous communities there were more prepared for the tsunami. Even though the previous event, how many hundreds of years before the
one tsunami event we found, I think it was some 1,700, 1,500 like that.
So they were able to transmit that knowledge over a long period of time to then be able to be on the higher grounds and protect themselves. Very interesting. So we'll shift a little bit. Other research you were telling me about. Let's see, some context. India for decades has spoken about becoming kind of a user, producer also of nuclear energy. And one obstacle in that transition is the disposal of nuclear waste. So radioactive nuclear waste. So you were involved with identifying what would be the best either geological or synthetic deposits, areas to safely dispose of waste. Can you explain what are the rocks that are best for that, and what synthetic possibilities there are as well for capturing radionucleotides? So this work we started much later, just 4-5 years back when I was doing the work in speleothems. So we started working on the same material, because this is calcium carbonate and basically the calcite and aragonite. So we wanted to see how this idea came up to our mind, that because we have what we use is unstable isotope of uranium thorium, because it's not stable, so it changes, it breaks down into daughter cell. So that then we thought that when it can trap the uranium, is it any
is there any possibility that these particular rock can absorb some more nuclides in that? So we started doing some work. We did some experiment studies for radionuclides. We exposed them to certain nuclides, radionuclides, and saw. And we were amazed to see that 90 to 95% of radionuclide were absorbed by this rock, the material of this rock, calcium carbonate. Then we took another project in which we want to do more study for different kind of materials. For example, we started with this calcium carbonate, then we did an apatite also, how this radiation is affecting the apatites. So likewise, we did a lot of studies in different kind of materials, natural materials we did this time. So first we tried to see what is the structural and vibrational patterns of these rocks, these kind of material, natural material, which we did Raman spectra and other studies, XRD, Raman, and we utilized a lot of experimental techniques to understand the structural and the vibrational properties of these rocks. And then we gave the radiation to different material and see how do they respond to that. So we are getting very good response, and we have done some work. In these ones we already published very good, 4 paper we have published using that data.
What are some of the conclusions or recommendations if there is going to be a nuclear waste?
So that based on that, what we did, we proposed that there are some materials, geomaterials, which can also be utilized as a geological repository to dump those radioactive waste, which will be, if we are using the nuclear power tomorrow, any radioactive elements, so you have to dump them, right? So you need some sort of geological proxies, repositories to dump them so that material doesn't come out, because their absorption capacity is so much. So we can learn from the nature. As I said that, I showed you these kind of rocks, right? Stromatolite. So the maximum uranium of India comes from Kadapa region. Kadapa region, where you have a lot of uranium in these rocks. So people started extracting the uranium. So now we have very big mines there in Kadapa region, Andhra Pradesh. So this is actually, it became a lesson because they have the absorption capacity of those radionuclides. So when they can absorb the radionuclides which were coming due to the bombardment of meteorological fall, so that kind of knowledge can be utilized, and if we can make some sort of a synthetic material also for nuclear reactors, for example. Because what happened in nuclear reactors also, when you expose them to the radiation, they do not stay for a longer time. Their phase transformation and how they are changing into the different material, they breaks down. So these kind of problems they also face. So these kind of studies also become a base for them, so they can also utilize. So there is an application of these kind of material which is best to use either for their nuclear reactors, either to dispose of the nuclear waste. So that becomes sort of a template to continue these.
And is there any risk in these potential repositories, geological repositories, of being some kind of leakage into groundwater or something like that, or these would be determined in places that are far off from any kind of water supplies? Because I think you mentioned that some of these areas where there are mines, things have gotten into the water supply, which can be problematic. But what are the recommendations for repositories from a geological standpoint?
Yes, that's a very good question, because we do see problems wherever they have mining. You also might have learned about it, wherever you have these kind of mining facilities, especially the critical minerals and radioactive minerals. So it gets dissolved into the drinking water because it's soluble. That's a problem. So that is known as geogenic waste or geogenic radionuclides, which are getting interacted. So you do have a lot of arsenic, uranium in drinking water sometime, depending upon what kind of rocks you have around. And when they are in rocks, water takes a longer time to interact with rocks, so slowly it will come, and some ppm level our body can digest and can release it out. But if you take it above that limit, then of course it's harmful for you. So when it's in natural process, it dissolves a very small amount of uranium. But when you start extracting the material in the minings, it gets dissolved more effectively because now it's in the broken form. and it get dissolved very fast with the water. It does contaminate the water. So they try to use the maximum protection, like some kind of layers, so it doesn't penetrate to the groundwater.
Right.
But still, after doing these many careful things, still there are problems around the village. What we found, that people sometimes have cancer, sometimes they have a lot of skin diseases due to these kind of extractions. Like you remember asbestos, then there was a ban in asbestos. People come to know that later on they are causing the cancer in the lungs. So these kind of things, when they start using the extraction, these kind of things for mining, if they do it for a long time, so it has consequences in longer term.
And I imagine those lessons need to be translated to the repositories as well, right? To be far away from the water supplies.
Yes, absolutely. So wherever they have to make these repository, we should make sure that it's not feeding it's not contributing to the groundwater. Like any groundwater or any aquifers are not connected directly to these ones. So all these things should be, needs to be measured and needs to be considered before, whoever construct these kind of repositories also or use these kind of things. Yeah.
So let's talk a little bit about some of the science outreach activities, especially rural outreach that you do both here at JNCSAR and through TWAS as well. Maybe you can just talk about some of your science outreach, science education initiatives.
Yeah, sure. Thank you. So, in our institute has started science outreach activities long time ago. Since 2005, when Professor C.N.R. Rao Bharat Ratna, he is the founder member of our institution. Also, he got the Dan David Prize in 2005, and then he thought that there is a need of training the village student, rural. So what he says, the real talent always comes from the rural areas. So he started looking the students, he started identifying the student from rural areas where he can get the brains, who is really not corrupted by all these city life. I should say that it's like they have the raw knowledge, but it's more clear. They have more clarity, and they can struggle more because they don't have any other option. Whereas if you compare, even today, our children has a lot of facilities, but the rural kids do not have much facilities. They are not, and some of them, you won't believe, when we do the outreach activity, they do not know what is Google search. They don't know what is a search engine. Still. So imagine in 2005. So he found that rural India has a real talent. Then he started doing these outreach programs. They used to go to different places, mostly in the interior villages and rural India, and started communicating with the students and the local people there. How important, because he want to, empower the student, as well as he want to give them the scientific temperament. That's very important, because education is something different, but scientific temperament is little different. It doesn't come with the subject. It comes with the kind of knowledge you have around you. Science is not only in the textbook, right? Whatever you see around you is science. So how to connect you from the nature, and how to connect that science, that kind of template they want to fix in their mind. So people started appreciating these programs. So there was a lot of huge demand from different villages to conduct these kind of outreach activities. So they started all over India. I got connected with them from 2017 onwards, and actively I also participate in science outreach programs now. So we have some flagship program of Professor C.N.R. Rao Foundation. So Professor C.N.R. Rao Foundation actually helps us financially, because we need a lot of financial support. So he supports us financially so that we can go to the rural places, and we organize these kind of science outreach programs, not for the students, sometimes also for the community.
I think you said this is an interdisciplinary team of
11? So 11? We have around 11, 12 scientists, dedicated scientists. He go everywhere. Every year we go to different places. Like we organize 10 to 11 programs in JNCs and out of JNC. Other than that, so we have done programs in, there is a place called Lakshmeshwar, which is in here, close to Dharwad in Karnataka. That's a flagship program, and there is another flagship program which is in Uttarakhand Himalayas. So we are associated with an NGO. It's called Himalayan Gramin Samiti, and they also helps us. That program is nice because that's a kind of residential program we make. So we invite more than like sometime 200, 400 students from different villages. And combinedly they come, they stay under one roof, and we go from JNC, and there are other scientists also from IIT Mumbai, and we have some scientists from IIT Roorkee, IIT Kanpur also, who joins us even from IISc, Indian Institute of Science. So group of scientists, they join. We all stay with them for 3 days and then interact with them. Sometimes the students are so curious that they engage us till 11 o'clock, 12 o'clock in the night. And we always carry a telescope also with us. So we explain them about different science and how the planetary system works. And then we have some experts who talk about the outer space, and then show them the planet, how the Saturn look, and they are so excited. Till 12 o'clock they will be talking with us, and 2 o'clock morning you will see them at the rooftop.
That's very exciting to see.
It's very exciting. It's a 3 days program, so each moment, each minute they spend with us, with interacting. Initially when we went to these places, they were like little hesitant to talk. But once, first day, they are little hesitant. But second day onwards, they don't leave you. They just want to talk to you all the time. They want to know so many things. And we also feel really nice that we feel that whatever knowledge we have, we should give them. Because that's how the knowledge passes. So this was the aim of Professor Rao also when he started the science outreach program. Professor Rao and Mrs. C.N.R. Rao, Indumati Rao, they were very interested in all these kind of outreach activities, and we also tried to connect it. Professor Waldia, my mentor, K.S. Waldia, Professor K.S. Waldia, he started this program in Uttarakhand. And then in between, after his demise, we were not sure how we will take it over, how we'll take it on. So I said we have to take his legacy forward. So again, I went to Professor Indumati Rao. I requested that if he can start the program along with Professor Raja. We went, and then she was very happy that we still can continue the program, and still we are continuing this program. And it has become a flagship program of CNR Rao Foundation.
And this is once per year, you're saying?
This program we have 2 times, one during the summer. So summer program is a residential program, and we do one program during winter time. That's not a residential. In that program, we go to village, different villages.
How much time do you dedicate?
So about approximately a week. So we go to different villages, mostly which are very far off from the roads, like far off from the town. So we go to villages, different schools, and in that school, 3-4 school will gather. Then we moved another day, another school, in other city. So again, some students. So that's why Mrs. Rao always says that don't call it science outreach program. You call it reaching out program, because they are not reaching out to you. You are reaching out to them. So we work for those who cannot reach out to us. We reach out to them. So it's not science outreach, science reach out program.
Reach out program. Got it.
Which makes really sense, because we are trying to reach maximum number of students we can. And we love doing that. We do a lot of scientific lectures, very interesting lectures. So we try to make it more and more like story based, so that they take interest. Not too much textbookish. What they see around, we try to connect everything together. So we have lecture series, we have demonstrations, practical demonstration, and hands-on training for the students.
That's amazing.
And they are doing wonderful. I mean, like, we see the change, we see the difference now.
So you're learning different forms of effective science communication.
Yes, yes, absolutely.
And having a diverse team go there, this interdisciplinary team seems to really help in that.
Yes, it's very helpful.
Kids can ask questions from many different perspectives and get answers.
So we have people from theoretical sciences background, we have people from physics, we have people from chemistry background, organic and inorganic both chemistry, and then we have people from mathematics also. And you won't believe, like, I myself felt it, I was really scared with maths, when I was a student. So when I heard the science outreach programs, the teachers who were teaching the mathematics. I thought, why did I left mathematics? It's so very interesting. I said, I wish you could have been my teacher and I would have never left mathematics. Because
teachers are important.
That's what. Teachers are very important. It is very important that how a teacher teaches to the student.
Yeah,
it depends, because many a time we say that, oh, my son or daughter has lost interest in some particular subject. So it is not the interest. I think it is a way of teaching the student, because if the teacher takes interest in her or his own subject, then only you can, make others also feel about your subject. If a teacher is not feeling his or her own subject, you are just teaching as a textbook or giving them notes, then how will they get, interest about your interest in inspired and interested? Yes. So that's important, that how you are communicating. Your communication skills should be really good. Then only you can become a good teacher to teach and to reach out to these students, because they can't sit for a long time. If you are telling them something, a chapter, if you are teaching them, or teaching too much technical language if you are using, then they want a simpler language. They want it like a story, and then they get engaged with, and you show them some sort of demonstrations, practical, which we do mostly. So they, like, you see their excitement, man. I mean, like their eyes, you see the excitement. It gets brighten up when they see some experiment. And for me, I take the rocks to them, and they see the rocks. They say, oh, this fossil, it lives only in the ocean, this animal. And how you find them in Himalaya? Can you imagine? Then they look astonished that why, how? Then if you tell them that Himalaya were not there, they are the youngest mountain, and how they come up, and how these animals which were living in the ocean are now, you see, at the height of 5,000, 4,000 meters. You tell them the story and they get excited and they learn in that excitement.
Gives some amazing perspective for the kids. So
it's just wonderful. So we also get excited with them.
Yeah, sure.
We double our energy when we see them, that they are asking questions and they are getting more involved in our work. So
you inspire them, but they inspire
you
as well.
Inspire us. I think they inspire us more what we inspire them. So
great.
we get a lot of energy, and we get a lot of motivation to do, another programs.
So I hope more researchers can get that experience. It's really beautiful.
I wish. We need more researchers.
Reaching out program.
Yes. We need more researchers. We need more youngsters to join hands with us and can spread the knowledge. Because now you see in science, very limited students are coming.
Yeah, sure.
They are getting more attracted towards humanity or towards commerce subjects. So we need to have some good communicator who can really communicate science and can motivate them to take science. They can develop the scientific temperament in the student. That's very, very important.
It's really important, just for a way of thinking also in our challenging times.
It changed your thinking. It's not only about the subject. The way of thinking is been changed, the kind of subject you are studying. If you study science, then you think in a different way. You connect it.
If you approach the world scientifically, at least.
Yes, your approach toward changes when you are a science student. That makes a huge difference.
Well, thank you for all the work you're doing. Is there anything else you'd like to share that you're working on? Well, these are the things I'm mostly working on. Well, it's great. I think it's a perfect place to end this InterDialogue, and thank you very much for explaining so many things.
My great pleasure.
For organizing this amazing visit as well. It's been a fantastic experience.
Thank you so much. Thank you. Thank you indeed.
No.
I do not have any heavy words to thank you, but that's the max I can say. It was wonderful.
Okay.
Wonderful. Thank you.
Thank you for joining us for this InterDialogue. You can subscribe to be notified of future episodes and by following us on our social media channels at the InterPlex. Visit our website, interplex.org, for more interdisciplinary and intercultural content, and to join our growing collaborative community.